I'm going to keep going with the notes now. This is where the conversation starts to get really interesting when we talk about current flow. Current, remember, as we just talked about, is the result of the flow of electrons. And as we just learned from the battery, the electrons will spontaneously move from the negative terminal to the positive terminal. That spontaneously happens. This is called electron current. This is the current of electrons. This is what actually happens. However, there's a really interesting story that happens at this point. And it involves Ben Franklin. Ben Franklin, as you know, was one of these guys that was standing out in a lightning storm with a kite. And he wasn't doing that because he was crazy. He was actually doing it, well, he might have been crazy, but he was doing it because he was doing research on electricity. And there's a really long story that I can tell you here that's interesting, and you should probably research it at this point. But here's the main point, is that Ben Franklin's research led to a lot of developments in electricity. And he did a lot of things right, and he was a very smart guy. Ben Franklin figured out two things. Number one, Ben Franklin figured out that there were positive charges and negative charges, that there were two kinds of charges. And that's really significant because they didn't know about the atom at that time. They didn't know about electrons. They didn't know about protons. But he figured that out. That's pretty smart. The second thing Ben Franklin figured out is that only one charge moves. Only one of these charges of these two is actually going to move, to transfer from one place to another. That's true, and we know that today. We know right now, today, that it's the electron that moves, not the proton. Okay? And hopefully you remember that protons don't move because they're in the nucleus, bound by the strong nuclear force, therefore they're not going to move. That's really cool because Franklin didn't know about any of this stuff. Protons and electrons were not known about back then. And so he knew there were two. There's a positive and a negative. That's what he called them. And he knew only one of them moved. And basically he had a 50-50 shot picking which one moved. And Ben Franklin happened to pick the wrong one. He thought that the positive charges move, which again, we know today that they don't because they're a proton. But he didn't realize that. He picked the positive, and because of that, we've gone with his wrong idea for quite some time now, especially in the electrical industry. We called Ben Franklin's current the conventional current. Conventional current flows from the positive terminal to the negative terminal. Now, think about what you just wrote there. Do electrons flow from the positive terminal to the negative terminal? Not at all. The only way to get electrons to go from positive to negative terminal is to do work through a chemical reaction or whatever else to get them there. In other words, this flow is opposite the direction of electron flow. This is conventional current. This does not actually happen. And you may ask the question right now, well, why are we learning about this? We're only going to talk about electron current in this class. That's the current that we're going to consider because that is what is actually happening. The only reason I teach you conventional current is because you might need to know it if you ever go into some sort of electrical industry. Because in this country, again, sometimes wrong ideas die hard. And we still use conventional current in lots of wiring diagrams and devices in this country. We still consider conventional current, even though it doesn't exactly happen. Look at this diagram. You'll notice that the flow of charge goes from positive to negative. That doesn't happen. Nothing in a current, nothing in a circuit flows from positive to negative. This is conventional current. This is the Ben Franklin current, the movement of protons, quote unquote. Remember, protons do not actually move. So, two types of current, electron current and conventional current. The symbol for current, we use the capital letter I, and the unit is the ampere, symbolized. Usually we just say amp when we actually talk about it, amp or amps. That's what we say for short. There's a formula for current. It's I equals Q over T. This formula is in your equation chart under the big electricity section. And this one happens to be in number 32. It's contained in number 32. I is current. I is our current. Remember, we use amps as the unit for that. Q is charge. We've talked about that before. Remember, charge is measured in coulombs. And t, of course, is time, measured in seconds, as it always has been. All right, so let's use this sample problem to talk about, well, actually, let's not talk about the sample problem yet. Let's talk about the equation and just the concept of current. The easiest way, and maybe perhaps it's too dumbed down, but the easiest way I can illustrate current for you is, let's just imagine, here's Frisco and here's Dallas. This illustration, by the way, is courtesy of Mr. Anderson. I did not come up with this one. Let's imagine that you have a bunch of people. We don't have to imagine this. This is true. There's a lot of people that need to get from Frisco to Dallas on a daily basis. They commute. So let's imagine there are 3 choices to get from Frisco to Dallas. Your first choice is a 1-lane road. Maybe there's construction being done, there's only 1 lane open, and it leads from Frisco to Dallas, but it's a 1-lane road. Only 1 lane for cars to go by. You could also take the access road on the tollway, next to the tollway rather. And of course, the third option is to take the actual tollway. Most of us, quite obviously, would probably pick the tollway, provided we have the money to do it. And the question is why? And I know you would probably say, well, it's faster. Well, that's true. But why is it faster? Well, the reason why it's faster, the main reason, is not because of the speed limit, it's not because there's no cops, and it's not because of no stoplights. The main reason is the fact that there are more lanes. This one, the tollway, provides the least resistance to traffic flow. It's easier to get through on this road because there's more options to take. It's harder on this one, and yet even harder still here. And if you stationed yourself in one place right here and watched as traffic passed by and simply counted the number of cars that passed you per second, which road would give you the highest number? Well, obviously it's the tollway, because there's 3 cars that can pass you at one time versus 2 here versus 1 here. You would get 3 times the number just about here, and maybe even more so because the cars are also going faster. So current is increased on a road that has less resistance. The point of current is simply the amount of, you can think about the amount of cars, but it's the amount of charge, the amount of electrons that are passing one point at any given time. And then we can go back and talk about voltage a little bit. Voltage is simply the total number of cars that need to get from here to here. Let's just say there's 3,500 cars that need to get from the top to the bottom. That voltage is what provides the flow itself. The fact that there are cars that need to get from here to here, that's the reason why traffic is flowing. The voltage is the same in each case, but the flow is different. The current, the traffic current is different. So current is the amount of charge that passes any unit or any point per unit time. So we can look at this problem. It says a lightning strike has a charge of 10 coulombs and a current of 10,000 amps. How long does it take to strike? Well, obviously this is the equation we're going to use because it's the one that we've just learned. And hopefully we recognize that they're giving us Q here. That's the charge. And the current is 10,000 amps, and that's I. They've given us Q and I. So if we plug those in, 10,000 is I, and Q is 10. They want us to solve for T. How long does it take? We're solving for the variable on the denominator. In order to do that, you would cross multiply, or really in effect what that does is these two end up switching places, and T is 10 divided by 10,000. If you do that, your calculator gives you 0.001 second or 1 millisecond. That's an incredibly fast lightning strike, and it brings about the point that it's the current that really matters in the effect of electricity. It's not so much the voltage that matters. Again, with this one, the voltage, the number of cars that need to get from one place to another, is the same on all 3 of these. But clearly, if let's say we wanted to cross the road on foot, I would rather do it on this one than on this one. It's much safer here because the current, the flow of traffic is much less. Even though we have the same amount of voltage, it's the same number of cars that have to get from one place to another. It's the same point with this charge. It's not so much the amount of charge or the amount of electrons that have to go through as it is the amount of time. 10 coulombs is a massive charge, and all of those 10 coulombs of charge in a lightning strike, if it strikes you, pass through your body in 1 millisecond. That's why lightning can do so much damage to your body. So this idea of current brings us into the idea of resistance. All right? Resistance, the definition of resistance is hindrance to the flow of charge. Hindrance to the flow of charge. Again, we can think about resistance in this example. This road hinders the flow so much more than this one does. It's much easier to travel on this one. There's less hindrance to flow. Hindrance to the flow of charge. The unit for resistance is the ohm, or ohms, and we symbolize that with the Greek letter omega. It looks like a horseshoe, like a funky horseshoe with horseshoe, I guess you could just say. This is the Greek letter omega. And Ohm's law is what describes resistance. Resistance is described by this law, I equals V over R, and it can be switched around. We could be asked to solve for any of these three. As far as the variables in this equation are concerned, I is current. We understand that when it's the same as it was up here. The two new variables, V is voltage, and the units there are volts, which is V, and the R is resistance. And again, the units for resistance are ohms. Another word for voltage that you might see is potential difference, and I talked about that in the first video. Potential difference. Now, this example here is a good example. It's a way to picture resistance, but clearly traffic flow is not anything close to the same thing as electron flow. You might be asking the question, well, what provides resistance in an electric current? Well, resistance is provided by lots of things. In an electric current, the biggest thing that provides resistance are the devices that we plug in up here. Any light bulb, microwave, whatever electrical device we have provides resistance to flow. And the reason is because at this point the electrons are giving up their energy. They're changing the energy, and that simply, it takes some time, it takes some energy. The electrons are going to slow down as they move through here. And it stands to reason that the more devices we put on here, and that's a really poorly drawn light bulb, but you get the point. The more light bulbs or whatever they are, the more devices there are, the more resistance is imparted to the circuit. Also, the wire itself has a little bit of inherent resistance in it, but we usually don't consider it in this class. There's all kinds of resistance to the flow of electrons. Let's look at this sample problem. It says, what is the resistance of a circuit with a 9-volt battery and a 3 amp current? A is amps, V is volts. So we have a 9-volt battery and a 3 amp current. They want resistance, right? So we want to find R. They gave us voltage, and they gave us the current, which remember is I. So we have I and we have V. We want to solve for R, and that is going to be this equation right here. Keep in mind that these two equations, both of these are number 32, and number 32 is stated in this way. It says I equals Q over T, which also equals V over R, right? It's sort of all the same equation. We could actually use both of these two parts if we have those variables. All right, but since we have V and I and we want R, we're going to use this part. I equals V over R. So our I is 3 and our voltage is 9, and we want to know what is the resistance. Once again, a good easy way to solve this, if you're solving for the one on the bottom, either multiply by R on both sides or do your cross multiplication, which makes those switch places. R equals 9 divided by 3, which is 3, and the units for resistance are ohms. 3 ohms is the resistance there. Pretty simple calculation. They won't always be that simple, but in that case it's pretty simple.